Okay, welcome back everyone. Today we're going to be looking at Chapter 4, Rational Functions. Now there's a couple sections here. We're going to be doing 4.1, 4.2, and 4.3, but they build so closely and so quickly off each other that I decided it would make more sense to put these all together into one video. In 4.1, we focus on the idea of what a rational function is and asymptotes. In 4.2, we combine this new idea with ideas from previous sections to sketch rational functions. And then in 4.3, we simply extend the idea further with the idea of inequalities. So the only really new thing is in section 4.1. The other two sections build this new thing with previous ideas. Let's go through the new stuff, followed by several examples. So a rational function is a function of the form r of x is equal to p of x over q of x, where p and q are polynomials. Now, of course, because we have division here showing up as the form of a fraction, we know that we cannot have a 0 in our denominator. Thus, q of x cannot be 0. That's not to say that q of x can never be equal to 0, simply that q of x cannot be the 0 function. Places where q of x is equal to 0, as we will see shortly, hold special places in the graph of the function. An example of a polynomial function may take the form of, let's say, r of x is equal to 12x squared minus 8 over 7x plus 4. The numerator and the denominator are both polynomials, hence a rational function. For the domain, we know how to do this kind of problem. We have to simply make certain that the denominators are not 0. So for the domain here, x plus 1 is not equal to 0, which means x is not equal to 1. In terms of interval form, this will either be all real numbers except for -1, or in terms of the unions of several intervals, -infinity up to -1, unioned with -1 to infinity. It will also often be important to rewrite the rational function as a single fraction. So in this case, I would rewrite this first piece as 2 times x plus 1 over x plus 1 in order to get a common denominator. Then I can combine these into one fraction, distribute, and then simplify. Written out this way, we can see it's more neatly in the form of p of x over q of x. This can be helpful when we're trying to determine one or more different properties of such a function. Let's graph a very basic rational function and get a sense of the kinds of things that may arise that could not have shown up in a polynomial. Now, in order to make this graph, we're going to make a table of values, as this is not a type of function we've seen before. My first instinct may be to plug in 0. However, we look and we see that 0 is actually excluded from the domain. So I would write undefined here. Okay, 0 won't work. Let's start at 1. Maybe we'll go 1, 2, and 3, and these all work. I'll get 1, 1/2, and 1/3, giving me the first 3 points for this function, making sure, of course, that I am labeling my axes and putting a scale on the graph. I can fill in here, here, and here. Okay, it doesn't seem like this pattern will stop. As I increase x, y will decrease because the denominator is growing larger. The larger a number I divide by, the smaller the quotient. There's no reason this won't echo in the negatives. -1 and -2, for example, will give me -1 and -1/2. Like so. But then the question becomes, well, 0 is this place where my function is undefined. what happens as I get close to 0? Let's try, for example, putting in 1/2 and 1/3. Well, if I was going to do 1 over 1/2, since I'm dividing by a fraction, I should multiply by the reciprocal. This gives me 2 over 1, or simply 2. So dividing by 1/2 gives me 2, and dividing by 1/3 gives me 3, which allows me to fill in points here and here. And what I see happening now is my function beginning to shoot upwards. And now I see why 0 won't work, because the smaller my x value becomes, and I divide by smaller and smaller numbers, the output becomes larger and larger. I'm going to grow very, very large, but I can never actually divide by 0, so I don't reach 0. A similar thing happens on the other side, and this is my function. From this idea, we will see two new things that we haven't seen before. The first one is this x value that is not reached. The function is approaching this value, but it's not actually hitting it. However, the function is shooting upwards as x gets much closer to this value. The other thing we notice is a similar phenomenon happening horizontally. The function is getting very close to 0, and it's always getting closer to 0, but it does not reach it in this instance. The idea in both of these cases, where as one variable approaches a specific value, the other variable grows very, very large, or very, very large negative, is called an asymptote. We can have a vertical asymptote or a horizontal asymptote. And in both cases, the idea is the same. An asymptote will happen when one variable gets very close to a specific number, and the other variable grows very, very large, either towards positive infinity or negative infinity. Let's get some more specific definitions on asymptotes. A vertical asymptote will happen if, as x approaches one specific number, y goes to positive or negative infinity. This arised in the previous example at x equals 0. So x equals 0 would be the vertical asymptote. If you have simplified the rational function, you will know a vertical asymptote will arise when your denominator is equal to 0. Because if I would be dividing by numbers very close to 0, in other words, very small numbers, then my output will be very large. Note that this only works if the function is simplified, because if the numerator and denominator equals 0, then I'm dividing something small by something small, and that is not going to make a vertical asymptote. It's going to make a whole. So we can see, for example, I may have something like this. This is a lot like the previous function, but I created a whole here. What this equation would look like would be y is equal to 1 over x multiplied by, let's say this is 2, x minus 2 over x minus 2. In simplifying here, I would want to cancel out the x minus 2's, and so as x approaches 2, nothing is different than the original function 1 over x. But exactly at 2, you cannot plug it in. Even though my denominator is very close to 0, because the numerator is also very close to 0, nothing unusual happens. And we will call this a whole. A whole arises when nothing unusual is happening in a graph outside of a specific point, but at that point, the graph is undefined. If I were to cover up this hole, you would never know that it was there. This graph looks like it's acting perfectly ordinarily. But if I remove the cover, we see that there's a point missing. This is the idea of a whole. Let's do an example here. I've got a rational function. I would like to find vertical asymptotes and wholes. So I will factor my numerator. Looks like it will be x minus 3, x plus 2. And my denominator, x minus 3, x plus 3. In this case, my instinct would be to cancel the x minus 3's. Because I am canceling here, this indicates a hole at x equals 3. X plus 3 indicates a vertical asymptote of x equals negative 3. Because here my denominator is 0, but my numerator is not. So at values of x very close to negative 3, I am dividing by a very small number. At here, x equals negative 2, I don't have any issues. If I plugged in negative 2, my numerator would be 0, but my denominator wouldn't. That's perfectly okay. We know that our function can be equal to 0, and in fact, that's an important value. It's an x-intercept. So we can put all of this together and get a rough idea, very rough idea here of a sketch of the graph. The points we care about are 3, negative 2, and negative 3. I'm not going to put a lot of detail in this. I just want to focus on the information we've gotten so far. At x equals 3, we've got ourselves a hole, which means that this graph is going to look like it should travel through 3 normally, but it will stop, have a hole, and then continue. At negative 2, we have a root. Nothing's wrong here. The function exists. It just crosses the x-axis, and we know that's perfectly okay. Negative 3 is where we have ourselves the asymptote. The function cannot actually exist at negative 3, but at values very close to it, our denominator is very, very small, whereas our numerator is not doing anything out of the ordinary. Dividing a regular number by a very small number gives us a huge number, hence the vertical asymptote. Now, this is how we find vertical asymptotes. We'll next want to focus on horizontal ones. A horizontal asymptote is the opposite idea, where the function is going to be going very large in the x direction, but y approaches a specific number. In this case, I would say that the horizontal asymptote would be the line y equals b. This should be a b here, not a c. Now, the idea in this case to find a horizontal asymptote is to think about what happens as x grows very large. And as x grows very large, the pieces of the polynomial that matter become less and less, because for large values of x, a squared term will not be nearly as important as a cubed term. None of those would be even remotely important compared to a term to the 4th or 5th power. In other words, only the high power matters. So if I was to take my rational function and think about very large or very large negative values for x, then we can simply pay attention only to the leading terms and nothing else. In other words, the end behavior of the rational function only cares about the leading terms. And then we can think about what happens if the numerator is larger, the denominator is larger, or if there's a tie. If the numerator is larger in degree, then because my numerator is growing faster than my denominator, the function itself is going to grow overall. There will not be an asymptote. The numerator will increase, which will make the entire function increase, and we will go up towards infinity or negative infinity, potentially giving us a graph looking something like this. Even though there's a vertical asymptote here, the graph is not leveling off. It's continuing to go in this direction and in this direction. Now, if our numerator has smaller degree, that means that the denominator is growing faster. And if I'm dividing by larger and larger numbers, then I'm going to eventually level off at 0, giving me a graph looking something like this. This is the asymptote that we care about. Now, if my numerator and denominator tie in degree, then they are both working hard to grow, and they're going to be growing at similar rates. This means that we will have a horizontal asymptote influenced by both the numerator and the denominator. In this case, you will divide the leading coefficients to get the horizontal asymptote. Let's take a look at a few examples here. In this first example, we are going to focus only on the leading coefficients, the leading terms, I should say, because I do care about the degree. In this case, my denominator has larger degree. 1 up here and 2 down here. Since 2 is larger than 1, and that's in my denominator, we will say that we have a horizontal asymptote at y equals 0. In the next function, the numerator is 2 and the denominator is 1. 2 is still larger than 1, but this case that 2 is in the numerator. That means that there is no horizontal asymptote. We would say that the end behavior is like a line. So we can say end behavior is like 4x squared over 3x, which would simplify to 4/3 x, which is a line with positive slope. This means that I don't know what my graph is doing in the middle, but we can predict what it's going to do in the end. Eventually, the graph is going to do something like this, looking kind of like a line would. Once again, we don't know what the graph is doing in the middle just from the end behavior, but we do know what it will be doing eventually. Finally, let's take a look at this final example. Once again, only the highest powers matter, and this time there's a tie, 3 equals 3. So that means that I do have a horizontal asymptote, and it will be y equals 2/5, because the 2 and the 5 are the coefficients. You can imagine canceling out these x cubes because they're the same. And we don't care about this stuff because only the highest power matters. Now, putting all of this together gives us everything we need to sketch a curve. Now, before we go into this section, I want to make a point here, which is that we are not going to use this curve sketch if we have a graphing calculator. Of course, a graphing calculator can make the sketch for us very easily and very quickly. I want us to understand some of the main points that a graphing calculator is going to do so that when you do use a graphing calculator moving forward, you understand what's going on. That being said, I do not want you using a graphing calculator when approaching these types of problems on your homework and on the exams. The first thing you're going to do is factor the numerator and denominator if you are able to do so. Once you've done this, your next task is to find the domain. Numbers that are not included in our domain are going to either be a whole, if that number would cancel with the numerator, or a vertical asymptote, if the number would not. Next, we'll find the x and y intercepts. The y-intercept we simply find by plugging in 0. The x-intercept we will find by setting the numerator equal to 0. Note that if any of these numerator values were wholes, then it won't actually be an x-intercept, but it will still be a place where our curve appears to cross or touch the x-axis. There will just be a hole at that location. Finally, the end behavior of the function is going to be determined by looking at the degree of the numerator and the denominator and comparing the leading terms, just like we did in the previous examples. The last thing we'll do is use a sign diagram just like we do when solving inequalities, to figure out where the graph is positive or negative. This will allow us to connect the dots of all these important values and determine a good sketch of the graph. Let's go through one full example in detail here. We're given this function. Our first step is going to be to factor. Let's say that we call this function h of x, and we can factor the numerator and the denominator. I'll first pull a common factor out of the numerator, x squared minus x minus 2, and then factor each. So x minus 2, x plus 1 over x looks like plus 3, x minus 2. Okay, so for the domain, x cannot be equal to negative 3 or 2. We can say that this is negative 3 and this is 2. Looking at the numerator, I get a 2 and a negative 1. So this means that I can classify each of these numbers. At x equals negative 3, we will have a vertical asymptote because the denominator is 0, but the numerator is not. At x equals 2, we will have a hole because I could cancel this term out if I was to simplify, meaning that I cannot plug in 2, but nothing unusual is happening at x values near 2. And finally, at x equals 1, the numerator is 0, which is totally fine, and we have a root, or an x-intercept. Next, we should plug in y equals 0, or excuse me, x equals 0. Plugging in x equals 0, we obtain 0 minus 2, 0 plus 1 over 0 plus 3, 0 minus 2, which gives us negative 4 over negative 6, or negative 2/3. So that means the graph includes the point 0 minus 2/3. This is the y-intercept. Next, we can go ahead and we can look for horizontal asymptotes. Here, I would actually like to look at the original function before I factored. In this case, 2 is equal to 2, so I have a horizontal asymptote of y equals 2, or 2 over 1. All we need to do now is make a sign diagram. Now, when constructing the sign diagram, we will need to put on this number line every place that the function had a vertical asymptote or a root, or a hole that should have been a root. We can put all of the holes on the number line to be safe. That way we won't have any ambiguity. So let's go ahead and do that here. So let's just give ourselves a little bit of extra space for this one. So our number line needs to include negative 3, negative 1, and 2. We'll make the chart here. So, test values, let's choose minus 4, minus 2, 0, and 3. And then we can construct this. Now, I'm going to ignore the x minus 2 when constructing the sign diagram because it cancels out. When constructing the sign diagram, you can focus on the simplified version, 2x plus 1 over x plus 3. So here's what I see. 2x plus 1 and x plus 3 are the things I'll need to focus on. In this case, negative 4 will make negatives here and here. -2 will actually let this one be positive, but this one will be negative. And then once I get to 0, both of them will be positive ever after. Thus, I get positives most of the time, but I will get out negatives here. I just realized that we dropped a negative in constructing the y-intercept because we have to get a positive at 0. So let's go ahead and fix that dropped negative of over here. This is a negative over negative, so this should have been a positive 2/3. This is now enough information for us to construct a sketch. So what we're going to do is we're going to first put on the asymptotes. We'll have to keep going back to check our work here. We can't fit it all on one screen, and that's okay. The most notable numbers occurred at the things that we originally put on the sign diagram. -3, -1, and 2. These will be points of interest. So, first, we'll take a look at -3, which was our vertical asymptote, at -1, which was our root, and at 2, which had a hole. So -3 was a vertical asymptote, -1 was a root, and at 2 we'll have a hole. We see that the graph is going to have a horizontal asymptote of y equals 2. So let's mark that in as well. Next, we'll have to look at where the graph is positive and negative. The graph starts positive. So that tells me that the graph is going to begin here and increase like this up against our horizontal asymptote. When it comes back, the graph is negative. That negative is going to be from -3 up to -1. Let's mark this on my sign diagram. So this was going to be positive here, here, and here, and negative here. I'm going to copy this sign diagram over so that we can take a look at it as we're constructing the graph. So the graph needed to start out positive until we reached -3. From this point, it will be negative until we hit -1, and then it will be positive again. So I would expect my graph to maybe come up from here. Over at -3. I hate when this happens. Pass through this root, and then it will be positive, and it will be positive the rest of the time. We had the y-intercept at 0, 2/3, so our graph can pass through this point as well. It doesn't look like it needs to do anything else strange. It's going to be positive. The only other thing we'll need to be careful of is marking off the hole at 2. We could figure out what the y value at 2 is supposed to be by plugging 2 in to the simplified function. Over here, we had the simplified function. So if we plugged in 2 here, 2 times 2 plus 1 over 2 plus 3 gives me 2 times 3, 6 over 5. So this hole is going to occur at the point 2, 6 over 5. There's nothing there, but it's clear what should be there, and it's a little bit above 1. Finally, we'll continue the pattern and make it clear that it's approaching the asymptote. And there's our sketch. There are a lot of pieces to keep track of in this type of problem, but if you organize yourself carefully, you'll make sure to get all of them. So once again, the things we cared about were the domain, vertical asymptotes, holes, and roots, the y-intercept and the horizontal asymptotes, and then a sign diagram. It's really only 1, 2, 3, 4 things to do after you've factored. As long as you keep yourself nice and organized, you'll be able to keep track of them easily because each piece is something that we've covered previously, except for horizontal asymptotes. And that piece is, of the pieces, one of the least complicated. Slow and steady, make sure you're organized, label your work, and you'll be good to go. Now, changing gears just a little bit, we want to look at inequalities. And the reason I say just a little bit is because we're going to be using techniques that we just used in order to approach this. Just like we did in the previous problem, we'll be factoring and setting up sign diagrams. We can solve the original equation and then use a sign diagram to determine the solution. Let's take a look. I've got this function, and my approach is going to start exactly the same as if I wanted to graph this thing. Factoring the numerator, I get x minus 4, x plus 3, and in the denominator, x plus 3, x minus 2. Great, let's get all of the important numbers. 4, negative 3, which appears twice, and 2. So these are the numbers that will need to appear on my number line. We can plug these numbers in and see what comes out. So negative 3, 2, and 4. 4 is going to be a 0 on my graph because the numerator is 0, but the denominator is not. 2 is going to be a vertical asymptote because my denominator is 0, but my numerator is not. And at 3, we will have a hole, which means that I wouldn't expect anything different to happen on either side, but the graph is still undefined at this point. From here, we'll just need to do test values again. So let's say negative 4, 0, 3, and 5, and we'll construct a sign chart. So let's go ahead and construct that chart over here. So we will put in first the test values, negative 4, 0, 3, and 5. And we will be using the simplified version, which will be x minus 4 over x minus 2. So these are the only factors I care about. X minus 4, x minus 2, and the final answer. So x minus 4 is going to end up being negative until the very end, when it will turn positive. X minus 2 is going to be negative for the first couple, and then positive once I reach 3 or higher. That means that I will be positive here, here, and here with 2 negatives or 0 negatives, but I'll be negative here with a single negative. Let's mark that on the sign diagram. So we will be negative only at the interval including 3, from 2 to 4. The rest of the time, we will be positive. Now, we could use this information to make a sketch of the graph, but we don't need to here. We just did an example of that. Instead, we can just simply use this to solve the equation, the inequality, I should say. Let's circle the regions that are supposed to be our solutions. We need this piece to be greater than or equal to 0. So we would like it to be positive. Thus, this region is good, this region is good, and this region is good. Because it's greater than or equal to, we'll want to include the points where it's equal to 0, which in this case is only here. Even though it's positive before and after this point, because it's a hole there, we cannot include -3 as a solution because the function is not even defined at -3. So I would say for our solution, we should put these intervals. -infinity to -3. -3 to 2, and 4 to infinity. And the only hard bracket will show up at 4 because at this point, the function is equal to 0. And we want it to be equal to 0, so we will include that point. All other locations, 3 we can't include because that's a hole, and 2 we can't include because that's an asymptote. And that is chapter 4. Have a great day.